Hello Math 1 students, this is section 12.6. We're going to prove triangles using the last two congruency theorems, ASA and AAS. So we're going to learn to use the ASA and AAS congruence theorems. So let's start with ASA, angle, side, angle. Two angles and the included side of one triangle are congruent to two angles and the included side of a second triangle, then the two triangles are congruent. Now notice you have two angles and here the side is included, which means the side is in between the pair of congruent angles. That is the included side. So in this case, if angle A and angle D are congruent, AC is congruent to DF, and angles C and F are congruent, you have the triangles ABC congruent to triangle DEF by ASA. Again, remember the letters of the triangles need to match up based on the corresponding angles and sides. Now, as I mentioned, for ASA, the congruent side has to be in between the two congruent angles. But what if the congruent side is not in between the congruent angles? So let's say AC and DF were not congruent to each other, but let's suppose BC and DE were congruent to each other. Now you can't use ASA anymore because the congruent side is not included. It's not between the two congruent angles. Are we stuck? The answer is no. We have another rule, AAS, angle, angle, side. So now you just need two angles and the non-included side. If those are congruent from one triangle to another, then the two triangles are congruent. In other words, if you have any two angles and a side, whether the side is in between the two angles or not in between, then you can use one of these two rules, ASA, AAS. So in these triangles, angles A and D are congruent, C and F are congruent, and now side BC is congruent to EF. Notice that that is not the included side. Nevertheless, by AAS, triangles ABC and DEF are congruent. So if you have AAS, you have two congruent pairs of angles. The reason this works is that by the third angles theorem, remember, the third pair of angles also has to be congruent. So you could have used ASA. So AAS is really what's called an offshoot or corollary of ASA. It's just another application due to the presence of the third angles theorem. Example 1. Can the triangles be proven congruent with the information given in the diagram? If so, state the theorem you would use. So let's take a look at 1A. What do we have? We have one pair of congruent angles. These two angles at the top, those are congruent based on the markings. We also have a pair of congruent sides by the markings. So the question is, are there any other pairs of congruent sides or angles? And the answer is yes. By the vertical angles congruence theorem, those two angles that are marked in red are also congruent. So we have two angles and the non-included side. Notice that the congruent side is not in between the two congruent angles. So therefore, we have congruence by angle, angle, side, AAS. 1B. So now what we have are three pairs of congruent angles, including a vertical angles. And the question is, are there any other congruent parts that we can identify? And the answer is no, because there are no sides that are marked congruent to each other. So we have three angles and we don't have any congruent sides, so we cannot prove that these two triangles are congruent. 1C, we have two pairs of congruent angles. We have the one on the top left and the one on the bottom right. That is one pair of congruent angles. We have another pair of congruent angles here, the ones with double markings. So we have two pairs of congruent angles. Is there anything else that's congruent? Well, you have this shared side in the middle. So that side is congruent to itself by the reflexive property of congruence. So now we have two angles and a side that is included. So therefore, these triangles are congruent by ASA. 1D, are there any other congruent parts? So we are given PQ is congruent to QR. We can also conclude that MQ is congruent to itself. So we have two sides, but there are no pairs of congruent angles, and we cannot conclude that the third pair of sides is also congruent. So again, we cannot find congruence. We only have two sides, but we don't have the third side, and we don't have the included angle. All right, here's a proof. Given AD is parallel to EC and BD is congruent to BC, we're trying to prove that triangles ABD and EBC are congruent. So let's start with statement 1. AD is parallel to EC. And that is given. Statement 2. Angle D is congruent to angle C. Now, why are those two angles congruent? By the alternate interior angles theorem. So it's harder to see in these pictures, but basically you have a transversal. Those are the two parallel lines. There is the transversal. So according to the alternate interior angles theorem, those two angles, angles D and C, are congruent. So that is why you're given the parallel lines. Whenever you see parallel lines, look for something like alternate interior angles to get you one pair of congruent angles. Statement 3, BD is congruent to BC, and that is given. So now we have a side and we have an angle. Next, we have the third part that we need. It's angle ABD is congruent to angle EBC. These two angles are congruent because they are vertical angles. So by the vertical angles congruency theorem, those two angles are congruent. So now we have two pairs of angles that are congruent and the side that's included. So let me mark these again so you can kind of see. So side BD and BC are the included side. Thus, statement 5, triangles ABD and EBC are congruent by ASA, angle side angle. 2b, given that AB is perpendicular to AD, DE is perpendicular to AD, and AC is congruent to DC, prove that triangles ABC and DEC are congruent. So first we'll combine the perpendicular segments into one, and those statements are given. So what happens is when you have perpendicular lines, they form right angles. So AB perpendicular to AD form angle A as a right angle. We are given DE is perpendicular to AD, so therefore angle D is a right angle. So those two are right angles. The definition of perpendicular lines. If two lines are perpendicular, they form right angles. Statement 3, therefore angle A is congruent to angle D because they're both right angles, and all right angles are congruent. That's the right angles congruency theorem. 4, AC is congruent to side DC, and that is given. And I want to mention again, you don't have to have the exact same order as long as it follows a logical step. So you could have had this statement number 2, and it would have been totally fine. Next, statement 5, angle ACB is congruent to angle DCE, and these are our friends vertical angles again. So by the vertical angle congruency theorem, angles ACB and DCE are congruent. So therefore, triangles ABC and DEC are congruent. And how are they congruent? Well, we have two angles, angles A and D, and we have the side in between. So those two triangles are congruent by ASA. So remember, angle, side, angle. Example 3a, we're given HF is parallel to GK and that F and K are right angles. Prove that triangles HFG and GKH are congruent. So we'll start with statement 1, HF is parallel to GK. And that is given. Next, angle GHF is congruent to angle HGK. And again, these are the alternate interior angles theorem. So again, let me show you. There is one transversal, there is another, and there's a line going between them. These two angles are congruent. So that's angle GHF and angle HGK. Next, we're given that angles F and K are right angles. Therefore, angles F and K are congruent because of the right angles theorem. All right angles are congruent. So we have two pairs of congruent angles. Finally, HG is congruent to itself in the middle, shared side of both triangles. And that is the reflexive property of congruence. A segment is congruent to itself. So statement 6, triangles HFG and GKH are congruent. What do we have? We have two angles and a side that is not in between the two angles. So therefore, these two triangles are congruent by AAS, angle, angle, side, angle, angle, and a non-included side. 3b, given that angles S and U are congruent and RS is congruent to VU, prove that triangles RST and VUT are congruent. Statement 1, angle S is congruent to angle U, and that is given. Statement 2, RS is congruent to VU, and that is also given. So we have an angle, we have a side. Where is that third corresponding part? And again, you notice that we have two intersecting lines. So angles RTS and angles VTU are congruent because of the vertical angles congruency theorem. So now we have two angles, angles S and U, and angles RTS and VTU, and a side that is not in between the two angles that are congruent. So therefore, triangles RST and VUT are congruent. That's by AAS, angle, angle, side. So as a review, here are the 5 congruency rules. So we have SAS, 2 sides that include an angle. We have SSS, all 3 pairs of sides are congruent. We have HL that applies for right triangles, and you have 1 congruent leg and the congruent hypotenuse. We have ASA, which is angle, side angle. The side that's congruent has to be included or in between the 2 angles. And finally, we have AAS, 2 angles and a side, but the side is not included. It is not in between the 2 congruent angles.